again, this one's question 7, which was about electricity. So the first one was actually talking about this kind of conductor that we had here, so an ohmic conductor, so tell me it obeys Ohm's law, connected to an ideal ammeter and a voltage supply. So I'm giving a few different bits of information: the density of free electrons, that's remember N, which is our electron density, our resistivity, and the dimensions of this, so width, height, and length. Okay, so just making sure we know that this is the length there and the width and the height, and just being really careful, these have been given in centimetres, so it's something I need to watch out for. So the first one was saying, the other one there, the ammeter reading is 2 amps. Again, that's kind of a little sneaky bit hidden there at the bottom. So the first bit says calculate the resistance of the conductor. So again, I'm using my resistance equal to resistivity, length divided by area equation. And at this point, I just need to sub in my value. So my resistivity from above, my length was 0.1, because that is given in centimetres and putting it into metres. And then the area, so the area is the cross-sectional area, so that's 0.2 centimetres times 0.2 centimetres. So I did 0.2 times 10 to the minus 2 to account for the centimetres, and then squared it all, which gave me 0.043 ohms given to 2 significant figures. The next question then was asking about the drift speed of the electrons given in centimetres squared. Centimetres to the second to the minus 1. So in this case, I don't have to worry about changing my units out of centimetres. I can leave those in. Now, it's simply asking the drift speed, so I'm going to use my I-nave equation. Remember, E or Q is just the electric charge, and we're dealing with electrons, so I'm just going to use my electric charge in that. If I resolve for V, okay, I've got I divided by NA E. So in this case, my current was 2. My N is my electron density, so I just had to get that from the previous data on the other page. Area is just 0.2 squared. I don't have to worry because it's in centimetres. And then E is my electric charge, so charge of the electron, so 1.6 times 10 to the minus 19, which again gives me 0.37 centimetres per second. The next question then was moving on away from electricity more into electric fields. And we had to talk about it was being in a uniform field between 2 parallel plates. Okay, so what it's essentially telling me here is it's almost like I've got a plate there and a plate here. Okay, with this one being my positive plate and this one being my negative plate. So it's like 2 parallel plates that they're going between. So when we use the electric field between 2 plates, okay, we could use the equation the electric field is equal to the potential difference between the 2 plates divided by the distance between the 2 plates. Okay, now to work out that potential difference, I just need to do V is equal to IR. Okay, and because I've got R from my previous answer to A, and I've got I being 2, okay, that comes out to be 0.086 volts. Okay, so that's my voltage going in up at the top. My distance, okay, the distance between the plates is the length of the conductor, so that's 10 centimetres, so that's 0.01 metre. Okay, so I'm going to put 0.086 divided by 0.1 to give me 0.86 volts per metre for my electric field there. Now the next one was a little bit tricky, and my kind of big tip with this is sometimes they get you to show these relationships and they might be something that you've not quite done in class. One of the big tips is if it comes up as a question like this, maybe by question set of D, okay, you want to start looking at the equations that you've used previously. Okay, so try and figure out how to do this. You can also look in and sort of look at equations that contain what you need. Okay, so I can see resistivity in there, so it tells me I'm probably going to have to use the resistivity equation. I've got velocity, so I'm probably going to have to use the I-nave equation. And I start to sort of figure out maybe which equations I have in here. So this is one way that we could solve this. So I said that voltage is equal to IR. Okay, it's also equal to the electric field multiplied by D, okay, by the distance. So that also gave me in there. Now remember, D in this case is length. Okay, so I can also sub that in for being length. And R we can give by the resistivity equation. So R is equal to resistivity, length divided by area. So I go with I rho L over A is equal to EL, and I can cancel my L's out at this stage. We also know that I is equal to nave, which is the electron density, the area, the velocity, and the electric charge. So again, I can sub those in up here. So I get NAVE, resistivity, divided by area. So again, my areas cancel, and that is equal to the electric field. In this case, we just simply have to do a rearrangement. Okay, so I bring my electric field down, so it's velocity divided by electric field, which is equal to 1 divided by n, e, and rho. So that's what we've got over here. I'm apologising because I accidentally put a little v in there. So that is equal to 1 over n, e, rho. Okay, which is what the equation was showing up here. Okay, so if you are a little bit unsure, have a little look what equations you might need and start just trying to sub them in. And you usually have to do some cancelling out for those. And that was question 7.